Learning objectives. In this lesson, you will be learning about searching, sorting, and complexity and the following in detail. Selection sort, insertion sort, bubble sort, quick sort, merge sort, heap sort, radix sort, and their complexity. Searching, sequential searching, binary search tree, ASVL trees, B trees, searching, sorting, and complexity. Searching, sequential and binary searches, indexed searches, hashing schemes. Selection sort. Selection sort is one of the O of n to the power of 2 sorting algorithms, which makes it quite inefficient for sorting large data volumes. Selection sort is notable for its programming simplicity, and it can overperform other sorts in certain situations. Algorithm. The idea of algorithm is quite simple. Array is imaginary divided into two parts, sorted one and unsorted one. At the beginning, sorted part is empty while unsorted one contains whole array. At every step, algorithm finds minimal element in the unsorted part and adds it to the end of the sorted one. When unsorted part becomes empty, algorithm stops. Let us see an example of sorting an array to make the idea of selection sort clearer. Example: sort 5, 1, 12, minus 5, 16, 2, 12, 14 using selection sort. Finding the smallest value in one array and paste it in another array. Next, swap minus 5 to 5. Compare minus 5 and 1. Finding the smallest value, swap 2 to 12. Compare 2 and 5. Swap 16 to 12. Swap 16 to 12. Swap 16 to 14. Once unsorted array is empty, the algorithm stops. Code snippets selection sort. The following code describes the flow of steps for selection sort. In snippets, users use array named ARR to sort the values. The integer values I, j, mini-index, TMP are the variables used for sorting. First for loop is used to travel the unsorted values. Complexity analysis. Selection sort stops when unsorted part becomes empty. As we know, on every step, number of unsorted elements decrease by 1. Therefore, selection sort makes n steps of outer loop before stop. Every step of outer loop requires finding minimum in unsorted part. Summing up, n plus n minus 1 plus n minus 2 plus 1 results in O of n to the power of 2 number of comparisons. Number of swaps may vary from 0 in case of sorted array to n minus 1 in case array was sorted in reversed order, which results in O of n number of swaps. Overall, algorithm complexity is O of n to the power of 2. Selection sort. Selection sort is one of the O of n to the power of 2 sorting algorithms, which makes it quite inefficient for sorting large data volumes. Selection sort is notable for its programming simplicity, and it can overperform other sorts in certain situations. Algorithm. The idea of algorithm is quite simple. Array is imaginary divided into two parts, sorted one and unsorted one. At the beginning, sorted part is empty while unsorted one contains whole array. At every step, algorithm finds minimal element in the unsorted part and adds it to the end of the sorted one. When unsorted part becomes empty, algorithm stops. Let us see an example of sorting an array to make the idea of selection sort clearer. Example: sort 5, 1, 12, minus 5, 16, 2, 12, 14 using selection sort. Finding the smallest value in one array and paste it in another array. Next, swap -5 to 5. Compare -5 and 1. Finding the smallest value, swap 2 to 12. Compare 2 and 5. Swap 16 to 12. Swap 16 to 12. Swap 16 to 14. Once unsorted array is empty, the algorithm stops. Code snippets selection sort. The following code describes the flow of steps for selection sort. In snippets, users use array named ARR to sort the values. The integer values I, j, mini index, TMP are the variables used for sorting. Post for loop is used to travel the unsorted values. Complexity analysis. Selection sort stops when unsorted part becomes empty. As we know, on every step, number of unsorted elements decrease by 1. Therefore, selection sort makes n steps of outer loop before stop. Every step of outer loop requires finding minimum in unsorted part. Summing up, n plus n minus 1 plus n minus 2 plus 1 results in O of n to the power of 2 number of comparisons. Number of swaps may vary from 0 in case of sorted array to n minus 1 in case array was sorted in reversed order, which results in O of n number of swaps. Overall, algorithm complexity is O of n to the power of 2. Insertion sort. Insertion sort belongs to the O of n to the power of 2 sorting algorithms. Unlike many sorting algorithms with quadratic complexity, it is actually applied in practice for sorting small arrays of data. For instance, it is used to improve quick sort routine. Some sources notice that people use same algorithm ordering items, for example, hand of cards. Algorithm. Array is imaginary divided into two parts, sorted one and unsorted one. At the beginning, sorted part is empty while unsorted one contains a whole array. At every step, algorithm finds minimal element in the unsorted part and adds it to the end of the sorted one. When unsorted part becomes empty, algorithm stops. When algorithm sorts an array, it swaps first element of unsorted part with minimal element, and then it is included to the sorted part. This implementation of selection sort is not stable. In case of linked list is sorted and instead of swaps, minimal element is linked to the unsorted part. Selection sort is stable. Let us see an example of insertion sort routine to make the idea of algorithm clearer. Example: sort 7, -5, 2, 16, 4 using insertion sort. For each iteration, one number should be sorted. -5 to be inserted. 7 greater than -5, shift. Reached left boundary, insert -5. 2 to be inserted. 7 greater than 2, shift. -5 lesser than 2, insert 2. 16 to be inserted. 7 lesser than 16, insert 16. 4 to be inserted. 16 greater than 4, shift. 7 greater than 4, shift. 2 lesser than 4, insert 4. The iteration should be the number of numbers to be sorted. The ideas of insertion. The shift down is one of the idea to sort using insertion sort. The simplest way to insert next element into the sorted part is to shift it down until it occupies correct position. Initially, the element stays right after the sorted part. At each step, algorithm compares the element with one before it, and if they stay in reversed order, swap them. Shifting instead of swapping. It is the most commonly used modification of the insertion sort. We can modify previous algorithm so it will write shifted element only to the final correct position. Complexity analysis. Insertion sort's overall complexity is O of n to the power of 2 on average. O of n in case of applying insertion sort to a sorted array. It is O of n to the power of 2 when shifting or swapping methods are used, and O of n log n for binary insertion sort. Therefore, first of all, a practical performance should be considered. In practice, insertion sort outperforms most of the quadratic sorting algorithms like selection sort or bubble sort. Code snippets. We show the idea of insertion with shifts in Java implementation and the idea of insertion using swaps in the C++ code snippet. This snippet shows how insertion sorting is working. Bubble sort. Bubble sort is one of the simplest algorithms for sorting. It is used in practice once in a blue moon, and its main application is to make an introduction to the sorting algorithms. Bubble sort belongs to O of n to the power of 2 sorting algorithms, which makes it quite inefficient for sorting large data volumes. Bubble sort is stable and adaptive. Algorithm. Let us see an example of sorting an array to make the idea of bubble sort clearer. Example: sort 5, 1, 12, -5, 16 using bubble sort. Compare each pair of adjacent elements from the beginning of an array, and if they are in reversed order, swap them. If at least one swap has been done, repeat step 1. You can imagine that on every step, big bubbles float to the surface and stay there. At the step when no bubble moves, sorting stops. Complexity analysis. Average and worst case complexity of bubble sort is O of n to the power of 2. Also, it makes O of n to the power of 2 swap in the worst case. Bubble sort is adaptive. It means that for almost sorted array, it gives O of n estimation. Avoid implementations which don't check if the array is already sorted on every step. This check is necessary in order to preserve adaptive property. Turtles and rabbits. One more problem of bubble sort is that its running time badly depends on the initial order of the elements. Big elements, rabbits, go up fast, while small ones, turtles, go down very slow. This problem is solved in the cocktail sort. Turtle example. Thought array 2, 3, 4, 5, 1 is almost sorted. It takes O of n to the power of 2 iterations to sort an array. Rabbit example. Array 6, 1, 2, 3, 4, 5 is almost sorted too, but it takes O of n iterations to sort it. Element 6 is a rabbit. This example demonstrates adaptive property of the bubble sort. Code snippets. There are several ways to implement the bubble sort. Notice that swaps check is absolutely necessary in order to preserve adaptive property. Quicksort. Quicksort is a fast sorting algorithm. On an average, it has O of n log n complexity, making quicksort suitable for sorting big data volumes. It divides the objects into 2 for every iteration. Algorithm. The divide and conquer strategy is used in quicksort. Choose a pivot value. We take the value of the middle element as a pivot value, but it can be any value which is in range of sorted values even if it doesn't present in the array. Partition. Rearrange elements in such a way that all elements which are lesser than the pivot go to the left part of the array and all elements greater than the pivot go to the right part of the array. Values equal to the pivot can stay in any part of the array. Notice that array may be divided in non-equal parts. Sort both paths. Apply quick sort algorithm recursively to the left and the right paths. Partition algorithm in detail. There are two indices I and j, and at the very beginning of the partition algorithm, I points to the first element in the array and j points to the last one. Then algorithm moves I forward until an element with value greater or equal to the pivot is found. Index j is moved backward until an element with value lesser or equal to the pivot is found. If I is lesser than equal to j, then they are swapped, and I steps to the next position. I plus 1, j steps to the previous one, j minus 1. Algorithm stops when I becomes greater than j. After partition, all values before ith element are less or equal than the pivot, and all values after jth element are greater or equal to the pivot. Example, sort 1, 12, 5, 26, 7, 14, 3, 7, 2 using quick sort. 1, 12, 5, 26, 7, 14, 3, 7, 2. Unsorted array. At the beginning, 7 is the pivot value. As per the algorithm, the steps moves. Notice that we show here only the first recursion step in order not to make the example too long. But in fact, 1, 2, 5, 7, 3 and 14, 7, 26, 12 are sorted then recursively. Complexity analysis. On the average, quicksort has O of n log n complexity, but strong proof of this fact is not trivial and not presented here. Still, you can find the proof in the worst case, quicksort runs O of n to the power of 2 time, but on the most practical data it works just fine and outperforms other O of n log n sorting algorithms. Code snippets. The snippets show how quicksort is working. It should be implemented using C++. The left and the right are pointers like we said in I and J. Heap sort. This chapter will refer exclusively to binary heaps, although different types of heaps exist. We examine the idea laying in the foundation of the heap data structure. We call it sifting, but you may also meet other terms like trickle, heapify, bubble, or precollate. Heap algorithm. Now, let us phrase general algorithm to insert a new element into a heap. Add a new element to the end of an array. Sift up the new element while heap property is broken. Sifting is done as follows. Compare the node's value with the parent's value. If they are in wrong order, swap them. Example. The figure shows how to insert into a following heap. Step 1. Insert -2 into a following heap. Step 2. Insert a new element to the end of the array. The figure shows how to insert a new element at the end of the array. Example. Step 3. In the general case, after insertion, heap property near the new node is broken. The figure shows after insertion, heap property near the new node is broken. Step 4. To restore heap property, algorithm sifts up the new element by swapping it with its parent. The figure shows to restore heap property, algorithm sifts up the new element by swapping it with its parent. Step 5. Now heap property is broken at the root node. The figure shows the heap property is broken at the root node. Step 6. Heap sifting. The figure keeps sifting the nodes. Complexity analysis. Complexity of the insertion operation is O of h, where h is heap's height. O of h equals O of log n, where n is number of elements in a heap. Implementation. The code illustrates the output of heap sort. The working principle of heap sort. Radix sort. Radix sort is a clever and intuitive little sorting algorithm. Radix sort puts the elements in order by comparing the digits of the numbers. The bin sorting approach can be generalized in a technique that is known as radix sorting. Position by position, either starting from LSB or MSB, group the numbers into buckets. When you move to the next position, again, reorder them for that position while keeping the order of the previous position reorders. Once all the positions are done, the whole list should be ordered. Example. The example explains step by step how the radix sort is working. For every sorting iteration, a value should be sorted. At the end, the sorted values are viewed. Time complexity. Worst case time complexity is O of kn. K is the count of decimal places. N is the input size. An implementation for radix sort. Find the maximum number in the given list to be used in loop termination part. Run the loop for each of the decimal places. Prepare the position counters to be used for reordering the numbers for this decimal place. Reorder the numbers in the TMP buffer and later copy back to original buffer. Move to the next decimal place. Searching. Finding the location of a data in the computer system is called as searching. The efficient storage of data to facilitate fast searching is an important issue. We shall investigate the performance of some searching algorithms and the data structures which they use. Sequential searching. This algorithm has the benefit of simplicity. It is difficult to get wrong, unlike other more sophisticated solutions. The code follows the convention. The algorithm itself is simple. A familiar O-n-1 loop to walk over every item in the array with a test to see if the current item in the list matches the search key. The loop can terminate in one or two ways. If I reaches the end of the list, the loop condition fails. If the current item in the list matches the key, the loop is terminated early with a break statement. Then the algorithm tests the index variable to see if it is less than size or not. Binary search. To find a value in unsorted array, we should look through elements of an array one by one until search value is found. In case of search value is absent from array, we go through all the elements. In average, the complexity of such an algorithm is proportional to the length of the array. Situation changes significantly when array is sorted. If we know it, random access capability can be utilized very efficiently to find searched value quick. Cost of searching algorithm reduces the binary logarithm of the array length. Binary search tree algorithm. Algorithm is quite simple. It can be done either recursively or iteratively. Get the middle element. If the middle element equals to the searched value, the algorithm stops. Otherwise, the two cases are possible. Searched value is less than the middle element. In this case, go to the step 1 for the part of the array before middle element. Searched value is greater than the middle element. In this case, go to the step 1 for the part of the array after middle element. The example explains how binary search is working. In binary search, it should be in sorted array. Our example taken is sorted array. Huge advantage of this algorithm is that its complexity depends on the array size logarithmetically in worst case. In practice, it means that algorithm will do at most log 2 to the power of n iterations, which is a very small number even for big arrays. It can be proved very easily. Indeed, on every step, the size of the search part is reduced by half. Algorithm stops when there are no elements to search in. Code snippets. The code describes searches for a value in sorted array. ARR is an array to search in. Value is searched value. Left is an index of left boundary. Right is an index of right boundary. Returns position of searched value if it presents in the array, or -1 if it is absent. Binary search tree. Let us see more formal definition of BST. Binary search tree is a data structure which meets the following requirements. It is a binary tree. Each node contains a value. A total order is defined on these values. Every two values can be compared with each other. Left subtree of a node contains only values lesser than the node's value. Right subtree of a node contains only values greater than the node's value. What four binary search trees are used? Binary search tree is used to construct map data structure. In practice, data can be often associated with some unique key. For instance, in the phone book, such a key is a telephone number. Storing such a data in binary search tree allows to look up for the record by key faster than if it was sorted in unordered list. In order to keep tree balanced and minimize its height, the idea of binary search tree was advanced in balanced search trees. Binary search tree, internal representation. Each node of binary tree contains the following information: a value, user's data, a link to the left child auxiliary data, a link to the right child auxiliary data. For basic operations like addition, removal and search, a link to the parent is not necessary. It is needed in order to implement iterators. Node snippets. It is a routine when the whole structure of BST is put into two classes. Main class, binary search tree, is a public interface, and BST node mean for private use inside the main class. This division is necessary because some operations like removal may result in an empty tree, which means that the tree even doesn't have a root node. Balanced binary tree. To overcome the problem in binary search tree, we need a balancing tree. Balancing means decreasing the height of the tree. Thus, our goal is to keep the height of a binary search tree O of log of n. Such trees are called balanced binary search trees. Examples are AVL tree, red-black tree. AVL tree, height of a node. The height of a leaf is 1. The height of a null pointer is 0. The height of an internal node is the maximum height of its children plus 1. AVL tree. An AVL tree is a binary search tree. For every node in the tree, the height of the left and right subtrees differ by at most 1. B-tree searching operation. The search operation is similar to binary search tree. Starting at the root, the tree is recursively traversed from top to bottom. At each level, the search chooses the child pointer whose separation values are on either side of the search value. Binary search is typically used with the nodes to find the separation values and child tree of interest, but not necessarily. B-tree complexity. At average case, the search insert delete operation takes O log of n. Same as the average case, the worst case also takes O log of n. Index searching. The purpose of an inverted index is to allow fast full-text searches at a cost of increased processing when a document is added to the database. The inverted file may be the database file itself rather than its index. It is the most popular data structure used in document retrieval systems used on a large scale, for example, in search engines. Search algorithms. We designed and implemented the class ArrayListType to implement a list and the basic operations in an array. Because this chapter refers to this class, for easy reference, we give its definition without documentation to save space here. Sequential search. It is also called linear search. The search always starts at the first element in the list and continues until either the item is found in the list or the entire list is searched. Because we are interested in the performance of the sequential search, for easy reference and for the sake of completeness, we give sequential search algorithm for array-based lists. Binary search. As you can see, the sequential search is not efficient for large lists because, on average, the sequential search searches half the list. The binary search algorithm uses the divide and conquer technique to search the list. First, the search item is compared with the middle element of the list. If the search item is found, the search terminates. Search element 75. First, we compare 75 with the middle element in the list. List of 5, which is 39. Because 75 is greater than list of 5, we restrict our search to the list 6, list 11. This process is now repeated on the list 6, list 11, which is a list of length equals 6. The following C++ function implements the binary search algorithm. Number of comparisons for a list of length n. The table shows the comparison of time complexity. Sequential search, binary search. Hashing. A hash function is any function that maps data of arbitrary length to data of a fixed length. The values returned by a hash function are called hash values, hash codes, hash sums, checksums, or simply hashes. Recent development of internet payment networks also uses a form of hashing for checksums. The following C++ function finds the key length. Collision resolution. Hash collisions are practically unavoidable when hashing a random subset of a large set of possible keys. For example, if 2,450 keys are hashed into a million buckets, even with a perfectly uniform random distribution, according to the birthday problem, there is approximately a 95% chance of at least 2 of the keys being hashed to the same slot. Therefore, most hash table implementations have some collision resolution strategy to handle such events. Some common strategies are described. All these methods require the keys be stored in the table, together with the associated values. Well-known probe sequences include linear probing, in which the interval between probes is fixed, usually 1. Quadratic probing, in which the interval between probes is increased by adding the successive outputs of a quadratic polynomial to the starting value given by the original hash computation. Double hashing, in which the interval between probes is computed by another hash function. Keys hashing to same address are kept in lists attached to that address. For each table address, a linked list of the records whose keys hash to that address is built. This method is useful for highly dynamic situations where the number of the search keys cannot be predicted in advance. Example records. Each character is a key. Each column is a linked list. Thus we maintain M lists with M list header nodes. We can use the list search and insert procedures for sequential searching. The time to compute the index of a given key is a constant. Then we have to search in a list for the record. Therefore, the time depends on the length of the list. Unsuccessful searches go to the end of some list, hence we have L comparisons. Successful searches are expected to go half the way down some list. On average, the number of comparisons in successful search is L/2. Therefore, we can say that runtime complexity of separating chain is O of L. Since the method is used in cases when we cannot predict the number of records in advance, the choice of M basically depends on other factors such as available memory. Typically, M is chosen relatively small so as not to use up a large area of contiguous memory, but large enough so that the lists are short for more efficient sequential search. Recommendations in the literature vary from M to be about 1/10 of N, the number of the records to M to be equal or close to N. The output is in non-decreasing order. Each element is no smaller than the previous element according to the desired total order. The output is a permutation reordering of the input. Conclusion. Thus we learned about searching, sorting, and complexity and the following in detail: selection sort, insertion sort, bubble sort, quick sort, merge sort, heap sort, radix sort, and their complexity. Searching, sequential searching, binary search tree, ASVL trees, B trees, searching, sorting, and complexity. Searching, sequential and binary searches, indexed searches, hashing schemes,